Okay, so how's everyone doing? How's that fourth assignment going? Hard? Easy? Easier than last year, I can tell you that much. It's been simplified a little bit, so if you find it hard, just be happy that you were born a year later than you could have been. Otherwise, you would have been doing the harder version of the assignment. The harder version had you reading all the data from MP3 files that were on disk. So traversing the entire directory structure and loading data off of MP3 files using an MP3 header reading library. That leads to all kinds of extra difficulties. Okay, so I guess before I begin, does anybody want to ask me anything? Yeah. What are tuples? Tuples are almost like arrays, except that they can't be changed. They're immutable. The syntax is very similar. So you say, 1, 2, 3. That's the tuple 1, 2, 3. So let's say t is equal to the tuple 1, 2, 3. And you can access the elements of a tuple by their index. So t at 0 is 1, t at 1 is 2, 3, and t at 1 is 2. The thing you can't do, so they're immutable, so you can't change them. If you try and change them, you get an error that says this thing does not support item assignment. They're sort of useful if you want exactly that, basically a sequence of items which nobody is ever going to change. So sometimes you might like read things off of disk into tuples. So some of the questions we did where we read like things like questions off of we split and made a list of questions. It would have been okay to use tuples for that because we're never going to change those questions. It's just turns out to be a little bit more convenient to use a list because that's what split gives us when we call string.split, we get a list back. But tuples would have been a fine thing to use there as well. Yeah.
Is there an advantage to using tuples over lists?
Well, there is one advantage that we'll see today, and that is that you can put tuples into different data structures. We'll see today, we'll talk about sets and dictionaries. So you can put tuples into sets and dictionaries. Without a little bit of extra work, you cannot put lists into sets and dictionaries, at least not in a useful way. And so that's one advantage. And the other advantage is it offers some form of protection against accidentally changing data that you shouldn't change. I guess one other thing to say about tuples is these parentheses here are not necessary. So that does exactly the same thing. It creates a tuple, 1, 2, 3. And one handy thing you can do with tuples is tuple assignments, where you say something like xy equals 1, 2. And that assigns the value 1 to x and the value y to 2. It's a sort of handy thing to do. Yeah?
Is that like a keyword final in Java? Is that kind of the same concept?
No, the keyword final in Java means different things depending on where it appears, but for a class it means you can't extend that class, for example. For a function or a method definition, it means you're not allowed to override that method definition in subclasses. So it's different than that. I don't know that Java has an equivalent type. I mean, Java has certainly, you can create things in Java that are like tuples. You can create classes that are like tuples, but I don't think there's anything in the language that's equivalent. And that's actually a sort of a sad thing, because what you often find yourself using in Java is some class called pair or something like that, which sort of like a two-element tuple. And you use it a lot as a crutch for when you want a function to return more than one item. So in Python, that's no problem. You just return a tuple with all the stuff you want to return. We did this already on assignment 1, where you wrote a method that took a function that took a length measured in, I don't know, feet, and you returned it as a pair, feet and inches, or something like that. Or maybe that was the example we did in class. I don't remember. But tuples are nice for that. Quickly returning more than one thing from a function in an easy way without having to add some extra cruft around it. Any other questions? Here's another handy thing about tuple assignment. Swapping two values in Python is a little bit easier than in other languages. You just do that tuple assignment there. That swaps the values of x and y. Okay. All right. So today I want to talk about sets and dictionaries. These are covered in the textbook, but I'm not really happy about the way they're covered there. I don't like what he says about sets and dictionaries. He says they're a great way to organize data, but actually a lot of what he uses them for in the textbook, you could do the same thing either using objects or using arrays. So not terribly exciting. The real power that comes from sets and dictionaries is how fast they are at what they do. If you use them the right way, all the operations on these things are really, really fast. So let's start with sets. Anybody here taking Comp 1805? Okay. Did you learn what a set is yet? So what is a set? Okay, so it's group is another scary word, and because it means something else in mathematics. So I'll say collection, a collection of things. Usually you call them elements of the set. And what are the two main properties of a set that distinguish it from, let's say, something like a sequence? Yeah.
Finite?
Nope, sets are not necessarily finite, although Python sets are, because we have a finite amount of memory usually in our computers. Unordered. So there's one keyword. There's no particular order associated with elements in the set. And what else? One more keyword. They are distinct. So sets, set is an unordered collection of distinct elements. And in discrete math, what's the notation you use to write down sets if you're writing them down explicitly? Yeah. Curly brackets. So let's see if that works. There. So that's how we can make a set explicitly in Python. You use curly brackets. It's clear the distinction there between those curly brackets and the square brackets that we use for arrays. Because if you stand far enough back, it's not always obvious. So those are curly brackets. So that makes a set that contains the elements 1, 2, 3. Let's try a bigger set. And that's a set that contains the elements 1, 2, 3, 4, 5, 6, 7, 8. Let's add something to the set. So now we have a set that contains all those things, and it contains 1,000. Let's add something else. I don't know, 1,000,000. So again, now the set contains 1,000,000. And now for the first time we see that there really is no particular order in this set. It just happened to be that the elements 1, 2, 3, 4, 5, 6, 7, 8, and 1,000 when we put them in the set, happen to be printed in that order of increasing values. But once we put in 1,000,000, suddenly that ends up at the front of the set for some when we list out the set. Yeah. Because sets are unordered, so there's no guarantee about the order the elements you put in there. There's no guarantee about which order they show up in. Yeah.
Can you try putting two elements of the same number?
Let's try. S.add 3. So what should happen? Yeah. So the elements have to be distinct. That's the definition of a set. So one of two things should happen. Either nothing, or there should be an error saying you're trying to add a duplicate element to a set. But it quietly allows that to happen and just does nothing to the set. 3 is already there, so it doesn't get added. Yep.
So, how does it, what's the process of actually putting the numbers into the set? If there's no order, how does it determine where they go in the set?
You don't have to worry about that. It uses, internally it uses a technique called hashing, which basically takes each number and munges it up and decides where to put it in an array internally, but that has nothing to do necessarily with the natural ordering of the numbers, which is why, for instance, 1,000,000 shows up at the front of this, thing. Okay. If we print sets, we get the same thing. And the other thing that we can do with sets, we can remove things. So let's remove 3. Now 3 is gone from the set. So remember these important things. Sets don't allow you to have duplicates. They don't specify any order. So for example, here, if we were to iterate over this set, they'll come out in whatever order. The iteration will happen in whatever order is convenient for the set. So I say for x in S, print x. Then they come out, in that order. But I have no control over that. Yeah. And we can mix types of things in sets. So we can add strings and integers to the same set. There's no problem there. Yeah.
Is it like a pseudo-random where it adds the next string?
It's unfortunately, it's not even that good. So you can't even rely on it being random. It's whatever is convenient for the set to work efficiently. Pseudo-random would be even more useful than arbitrary, which means something that's convenient. Pseudo-random, you can't even rely on it being random because you saw it's pretty unlikely that if it were really random that 1, 2, 3, 4, 5, 6, 7, 8 would end up in exactly that order in the set. Yeah. If I was adding what?
If you add a duplicate to a set
Yeah.
in your script, and you try to run it, will you report an error?
No, we just saw that. If you just say add 4, that's already there. It just quietly does nothing. Yep. Yes. So you can ask for the list. So S is a set. We can ask for the list S, and we get back a list in some order. And we can also take an array. So let's say A equals range 10. A dot append hello. So A is an array. We can take A and turn it into a set. Now, what if we take a list and turn it into a set and turn it back into a list? Do we get the same thing back? Yeah.
Does turning into is that going to rearrange it at all?
Several things could happen. So we may not get the same thing back for more than one reason. So one is there's nothing about arrays that says you can't have the same element more than once. So in that array or list A, the element 3 appears more than once. So if we turn A into a set, well, one of the occurrences of 3 is gone, says the duplicates don't go in there. And then if we turn it back into a list, of course, it doesn't remember that 3 should appear twice. It's gone for good. And the other thing is the ordering. So if you take a list that's big enough and you turn it into a set, well, you get it in some different order than things come out in different order than they were in the list. And so you have that happen. We can, yeah, so you can't rely on the ordering, and this operation is not a self-inverse. You lose some stuff when you turn it into a set. Yeah? You may or may not get the same order the second time. It's not clear even what happens, so let's try. So if we take A to be the range of 20, and then we turn A into a set, well, we get a set that seems to store it in that order. So what if we take A to be the range of 20 down to -1, counting by -1, or let's call that B. So B, no, should have started at 19. A and B, there's two lists that contain the same things, right? So if we take the set of A and we take the set of B, they end up coming out in the same order now in the set, because that happened to be convenient for this kind of set. So in particular, the order inside the set has nothing to do with the order they appeared in the array. In one case, it was completely reversed. But it's best not to even think of things in sets as having any order associated with them. Okay, so the things you want to do with sets are adding. So fast operations are add, remove, and the in operation. So where's our set S? We can ask, is 4 in the set S? What's the answer? True. There it is. It's in that list of things. Is 3 in the set S? False. Okay. So when you use sets, these are basically the 3 operations you should be using, because these are the 3 operations that are super fast on sets. We're going to do a little bit of analysis of running times of things later in the course, but what I can tell you is that no matter how big your set is, so it doesn't matter if your set contains 20 elements or it contains 20 million elements, it's just as fast to add, remove, or check if something is in the set in either case. So the time it takes to check if something is in the set is actually independent of the size of the set. So that's a really powerful thing. So you can take, all the data in the world, put it into a set, and you can check if one particular piece of data is in there that's just as fast as if the set only had 20 things in it. Okay. And so we'll see what we can do with this. So let's go to our favorite example. So here we have a list of words. And we've done a few games with this before. So what's the length of this word list? It's 99,171. And we've played a few games with this before. So for example, we wanted to look for palindromes. So we've we can use a list comprehension for that and say, give me every word W for W in words, but only if W is the same thing as W reversed. Word list. And then we get all the palindromes, which are always often funny words. That's good. And all right, so let's try a similar thing, which is finding the anonyms. So an anonym is almost defined the same way as a palindrome. So a word is an anonym if you reverse it and you get another word. So you get a word that's in the dictionary. Okay? So let's see that. We want to keep the word W if, when we reverse it, so that's what we have here, if that is also a word, which means it's also in the word list. So let's try that. It's taking a while. So why is this taking so long? Yeah.
Because each word has to go through the entire list. Like, each of the individual words. How many words are in this list again?
About 99,000.
Yeah, so all the 99,000 words has to check with all the other 99,000 words every single time you check a word.
Yeah. So pretty much what's happening is this is a list comprehension that goes over every word W in this list, and it reverses it, and then checks if that reverse thing is in the list. And lists are not particularly fast at checking if something is in them. The way you check, the way that Python checks if something is in the list is it just goes through it, item by item, looking for it. So if we think about this for a minute, we can pull up. I said about 99,000 items, words in the list. So that's how many different values of W we're going to check. And for each one of those, we have to check it against the 99,000 elements in the list to see if it's reverse, it matches that element. So what do we got here? 1, 2, 3. 1, 2, 3, a million. 1, 2, 3. So about 9.8 billion checks are being done to check if these things are in there or not. So, given what we've learned, what I've just told you, what is a more efficient way to do this? Yeah?
Using a set?
Using a set. Because which part of using a set will make this faster? Yeah. Well, not so much the duplicates, because there's not so many duplicates in this list of words. There may be a few duplicates because we converted everything to lowercase, so there are some words that will, maybe one started with a capital A and the other one started with a lowercase a, and now it's the same word. It's not the duplicates so much, it's which part of this? Yeah. So the set arranges them for efficiency. For what operations? Searching. So adding, removing, and checking if something is in the set. So what's killing us there? We finally finished. We found all of these things. What's killing us here is this checking if the reverse of each word W is in the word list. That takes 99,000 comparisons. Sets can check this in some time that's completely independent of the number of words in the list. So let's see if we can do that. So let's say word set is equal to the set you get from the word list. Super fast. Now we go back to the same piece of code, but we take this check here, and now we're asking if a particular element is in a set instead of a list. Done. Yeah.
How is the amount of data independent from how long it takes?
That's the magic of the technique called hash tables, which Next year, when you take Comp 2402, you'll learn about how hash tables work. But it's basically, it's a trick to take these things and pack them into an array in a way that you can find them quickly. Yeah?
You said sets don't order things, but these look like they've been alphabetically ordered.
Well, these are alphabetically ordered because we iterated over the word list. So we're taking a subset of the word list, which was in alphabetical order, and just keeping the things that are that pass the test. The test is over here. That's what we're using the set for. And if we instead iterated over the word set, then indeed things come out in crazy order, because the iteration happens over well, it happens in a different order. Yeah. Well, a hash table is a way of implementing a dictionary and a way of implementing a set. Okay, so hopefully now you're convinced by this. We basically took something that took, I don't know, at least a minute to finish, a piece of code that took a minute, and we converted it basically just by using a set, no real effort on our part, to something that finishes in a tiny fraction of a second. I mean, from the time I hit enter till the time the results appear, there's no noticeable difference at all. This kind of thing is the sort of thing that distinguishes serious, good programmers from hackers. So start paying attention now. There are, some people who can make things work. They're hackers. They learned how to program often on their own without anyone pointing them into these sort of pitfalls you can get into. So knowing about how to use sets, for example, to take a piece of code that takes a minute or two and turn it into a piece of code that takes probably something like 1/100th of a second, that's what makes you a good programmer. That's what makes you an extremely valuable programmer. And it's also the kind of thing that separates a really good product from a really crappy product. So it's the kind of thing that makes your smartphone a pleasure to use, because instantly it comes up with suggestions and spelling suggestions and automatically completes your email list very quickly, versus something that every key you press ends up just chugging away with a little spinner there waiting for the something to happen. It can be the difference between a company that ends up becoming $1 billion company and a company that flops out of the gate. So this seems like a small thing, but it can be a huge difference. Okay. All right. So sets, the important thing to remember about sets is that they are fast for adding, removing, and checking if things are in the set. Other than that, there's not too much else you want to do with sets. So they're useful if you need to keep a collection of these things. They're not even good if you want to print them often. They're not great for that, because they have this issue that things get printed out in this weird order that you have no control over. That's usually not what you want. And I recommend that you ignore the Python documentation for sets. Because again, the documentation just tells you everything that sets do, and it's not including a bunch of things that are not so efficient to do. So basically, with sets, you want to more or less do the three things that I talked about: adding, removing, and checking if something is in one. So don't go looking for more exciting stuff that sets can do. There isn't anything more exciting than that. All right. So any questions for me about sets? So it's basically two ways to create them. Either you can create them explicitly using curly braces. That sort of runs out of, stops being fun very quickly because you can only create sets that you're explicitly willing to write out that way. The more common thing is you turn a list into a set. And then all the different ways you can create lists, either through list comprehensions or by splitting strings, which come from files and so on, you can do all those things to create sets as well. All right. Next up are so-called dictionaries. In Python, these are called dicts. So Python has this thing called a dictionary. I'll pronounce it dictionary to avoid confusion. And dictionaries are an interesting thing. What they do is they define what's called a map or a partial function, or what some of you think of as called a hash table, from a set of keys onto values. So maybe best is to do an example. Let's create a dictionary. And we'll say this dictionary at Goog, we'll put the string Google. This dictionary at MSFT, we'll put the string Microsoft, and this dictionary at Yahoo, we'll put the string Yahoo. And we can look at this dictionary now. It prints itself in a sort of funny way. It kind of looks like a set. So it's got the curly braces around it. But if you look carefully, you'll see that the items come in pairs. So the pairs are separated by a colon, and the stuff that comes before the colon is called the key of that pair, and the stuff that comes after the colon is called the value for that pair. And they have a lot in common with arrays. So you saw that we can set the values of a dictionary by using this, d@ syntax to set things. And we can look up the values in dictionaries. So if we look up D at MSFT, that's Microsoft. That's the string that MSFT maps to, is the string Microsoft. And so I said that a dictionary has a set of keys which map to values, and that's sort of by necessity. So a set implies that all the keys are unique. You can't have the same key appearing in there more than once, and that's because, well, if the key MSFT could be in the dictionary more than once, then what would this evaluate to? I mean, it could map to two different values, and we would never want that. So we can change the values associated with the key. We can reassign them. So that resets the value associated with MSFT, resets it to Microsoft Inc. Somebody give me a four-letter code for a company.
APPL for Apple.
APPL. So what do you think happens if we do this? So we get something called a key error. So we get a key error because APPL is not a key in this dictionary that we have. Okay? So usually we want to avoid key errors, or if we don't want to avoid them, we can always use try and except to catch them. But usually a key error is somehow an indication that something we did, we should have done differently for the item that's not there. And so for that, we still have, you'd usually use some kind of if statement where you would, before looking at the key, you would ask it, is that key in the dictionary? So this dictionary is we said that the keys form a set, and like a set, it's fast to check if something is in there. So when we ask if apple is in the set, it says false, and it says so very quickly. Not surprising because it's a small set, but it wouldn't matter if it was a big set. On the other hand, is why-who in there? Yes, it is. There's why-who, the key there. Okay. So we can very easily NASDAQ listed. Open a file. So here I've downloaded a file which has a bunch of stock ticker symbols. First thing in there is the ticker, the actual symbol, and then the next thing is the name of the company. It's a CSV file, and the separator is this vertical bar. So we know how to handle these things. We can say tickers equals T for T.split on the vertical bar for T in tickers. Okay, so so now we've got this giant list of these things. And a common thing that you might want to do if you're a stock person, although if you're a real stock person you would know most of these anyway, is to, as you see a number, something scroll across the bottom of your stock taking screen, you see these little four-letter things, and you might like to know, okay, what company is that? That looks, something interesting is happening to this thing. Give me some details about that company. And that's the kind of thing you do with a dictionary. So we can build a dictionary out of this thing. Like this. We'll say, I don't know. D is, start with a fresh dictionary and say for A in tickers, D at A at 0 equals D at A at 1. So what am I doing here? I go through this entire list of all of these stock, all of these company records, and I look at element 0. That'll be this thing here, the code, and I set that to element, assign element 1 to that. So this will give me a dictionary which maps the codes. So the keys are the codes, and these things are the company names. Oops, sorry. That was silly. There. So it's not D at that company name, it's just the company name. So we can try a few of these. One that we know is there is D at AAIT. And we get iShares, MSCI, whatever. Let's see if Yahoo is in there. Do you think it's there? It's not there. Is it really not there? Yeah. it is there, but you have to be very careful with these keys. They have to match exactly, and in this case, you know, all of these things are capitals, and so you have to be careful with this. Now, when you're designing an application, often you would like to make things easy for the user, and you don't want them to have to put these things in all caps all the time. Or maybe they can mix upper and lowercase. That shouldn't really matter because, well, for whatever reason. And so usually that means when you make your dictionary, you would do something like this. Put them all in, let's say, as lowercase. And anytime someone makes a query, you convert the query to lowercase as well. So, you know.
Would it be simpler just to convert the query to uppercase instead, since we're already all in?
If you can count on that file only having all uppercase keys in it. I'm not sure if it does or not. So as a safety measure, it doesn't hurt to convert them either all to uppercase or all to lowercase, but you should do it when you read the file and when somebody makes a query as well. So we can still do things like, you know, if the query is Yahoo, we can still ask for D at that query dot lower, and we get a reasonable answer. So if you were designing an application around this, that's the sort of thing that you would do. All right. Any questions? Yeah. That's an excellent question. What is Varney the Vampire? Well, it's also known as the Feast of Blood. And it's a romance of exciting interest. So it is one of the longest books written in the English language. It's pulp fiction from, I don't know when, it's no longer under copyright, which is why it's a useful piece of data for playing with. So it's an old pulp fiction book from, I don't know, sometime in the 30s or something. And you see that this edition that I got here, it came in many volumes. This particular one that I have has the first 4 volumes. 2, 3, and 4 are free with this edition. So the people who bought this were very lucky. So maybe we can, I don't know, do some I don't know, literature, archaeology, and study this thing, or mine this thing for data, and learn about what vampire books were like in the 1930s. Apparently there was a lot of romance in them, so that sounds like vampire books today, I think. Yeah, usually they're not really horror things anymore, right? They're romance things, so somehow that's come back. For a while they were a little bit more scary. Now vampires are fun. Good lovers, I guess. And so we can maybe learn something about these things. So let's open Varney. I happen to have a copy of Varney here. Well, let's see. So right now, Varney is a string. So it's not a huge one. If we had all the volumes, I think they consist of over 1 million words, but this string only has about 1.8 million characters in it. So at about 5 characters per word, or 6 characters if you count the space, we can get an estimate on the number of words by dividing by 6. So, you know, about 314,000 words. So we'd like to learn something about what vampire novels were like back then, but we're lazy and we don't want to read this whole book. And we don't want to read all 14 volumes of this book for sure. So let's see what we can get done in this class. All right. So the first thing I want to do is split Varney into words. And there's different ways we can try to do that. But most of them, if we try string.split, we're going to end up with lots of problems. So let's try string.split, which by default splits on white space. So let's try Varney words is Varney.split. And let's take a look at Varney words. Let's take a look maybe at the first 100 words. So actually, this is all front matter preface stuff in the book, because it's the first 100 words. It tells you that this book came from the Project Gutenberg, which preserves out of copyright books and makes them freely available. So that doesn't really tell us much about what we're interested in. So let's dive 5,000 words in. Okay, so that looks like a pretty good split, but let's look maybe at 20 words. One has to be very careful doing these examples in class because we're just jumping to random passages in here. So hopefully I'm not offending anyone. And remember, the book was written a long time ago. So it may not be politically correct by today's standards. Well, one thing that I see is they don't use a lot of punctuation. Because if they did, we would see, let's try 50-50 to 50-100. There we go. So we see one problem there. Our words also include punctuation marks, because string.split, if you don't give it any arguments, it'll split on it'll just split on white space, so we get punctuation marks showing up there. So what I would like to do is a little bit better than that. And for that, I'll import the Python regular expression module. So regular expressions are this great, terrific way of defining strings or defining patterns that match certain strings. And one of the things in this regular expression module is a split method. And what the split method takes is a pattern and a string as an argument. So in this case, the string, I think, is Varney. Where did you go, Varney? Yeah, Varney. And this pattern here will maybe cover some bits of regular expressions later. But this particular pattern matches a non-word character. So anything that is not a letter or a digit will match this thing. So it says anywhere there's a letter or something that's not a letter or a digit, split at that and then take it out of the input. So let's try again with that. And we'll just call this VW because I'll get tired of writing Varney words. So 477,000 words there. And if we look at it, now it's, we've lost all punctuation, we've lost all white space, but the thing is really broken up into just a sequence of words now. And so let's go from 6,000 to 6,050. Okay, and of course it's some sexy passage again. I'll skip that. It is a romance novel. But now we've got a good collection of these words. So here's a simple task. Sort of first order analysis of this would ask us, well, what are the most common words that are used by this author? And in fact, I suspect it's a collection of authors writing this stuff. So we would like to know, the most common words. Maybe before that, we could even ask, how good is this writer? And one measure of how good the writer is maybe knowing the size of their vocabulary. So how would we figure out the size of the writer's vocabulary? Yep. Yes. So let's see. Let's turn VW into a set and ask for the length of that. So 12,080 is the size of, 120,080 is the number of words in this set. No, 12,080. 120,000 would be incredible. So 12,080, that's not very big. So if you've ever, I don't know if you've ever heard of the, what is it? It's called the Upgoer 5 text editor. It's this text editor invented by or thought up by the creator of the XKCD comic, which only lets you use the 10,000 most popular words in English. And it's incredibly difficult to write anything complicated in it. 10,000 is not a huge vocabulary. We could compare that, for example, Gutenberg, let's say War and Peace. See if Tolstoy has a better vocabulary. No. Yeah. Equals. Okay. So War and Peace is 758,000 words. Let's make sure we got that right. 5,000 to 5,050. Okay, and if we convert War and Peace to a set, do you think he has a bigger, do you think Leo Tolstoy has a bigger or smaller vocabulary than the author of, significantly bigger, so 17,000 different words instead of the 12,000 in Varney. Remember, this was pulp fiction, cheap books printed on cheap paper, so meant to provide good value. So you paid 5 cents for one of these things and you got a lot of reading in. People didn't have TVs back then, right? So they needed some way to use up their time. All right, so we have an estimate of this writer's vocabulary. What if we wanted to know, let's say, the frequency with which certain words occur? So for example, if we look at current vampire novels, there's certain words that come to mind. Things like fang, blood, I don't know, death, these kinds of things. And we'd like to know, were those popular themes back then? So what we would like is to know for every word how often it occurs. Any tool for doing that? Sets, dictionaries. Yeah.
You could use the sets to find out all the individual words that aren't repeating.
Yeah.
So like search against.
Yep.
And then search for the frequency of those words in the set against the full.
Okay, so let's try that. Let's say VW set is equal to the set of VW. We know that there's 12,000 in there. And Then we want to do something like, let's say, we'll create a pair, which is the word, as well as the W dot count, how many times that word occurs in VW. For W in VW set. Okay, let's go over this slowly. We're going to, for every word W in the set, so there's 12,000 of those, we're going to create a pair, which is the word, and then we'll ask the list, VW, that's the list of words, that's the 480,000 or so. We're going to ask it to count how many times that word occurs. Okay? So, and we'll save that to counts. Yeah, we're creating a tuple. We're creating a whole bunch of tuples. Yeah.
Wait, so you're counting every single, how many times every single word?
Yes. And this is taking a while. So this seemed like a reasonable thing to do, but let's think about it for a second. Varney is, how many words in there? We said about 500,000, right? 480,000 or so. And the number of distinct ones is 12,000. So this VW.count, this is the list of words here, VW. This is the list of 480,000 words. And it asks us to count how often, it has to count how often this word W occurs. So it has to go through that list of 480,000 things, checking if each one is the same, is equal to W, and counting that. So let's see how much work we're doing. And it has to do that as many times as there are distinct words, which is 12,000. So again, we can get a rough estimate of how much work this is doing. It is about 12,000 times 480,000. So it finished, but it took a while. And so that's because it had to look at 1,000, 1,000,000, 5.7 billion comparisons of strings for that to work. I mean, this finishes now because, this is a fairly fast laptop. It did those 5.7 billion comparisons in whatever that took, a minute or two. But I don't like taking a minute or two. I want this to be I want this to happen faster. So what can we do to make, and we can look at counts, let's say, counts at 0 tells us, well, for some reason we sometimes get the empty string, which occurs a lot of times. That's not particularly useful. Counts at 1 tells us that the word aided appears 5 times in the text. 2, unscientific occurs once in the text. 3, pathless occurs twice in the text.
Can you find the ones that occur the most?
Yeah, so this is not particularly interesting. Now we have 12,000 of these things to go through looking for the ones that occur most. So we'll want to reorganize this, but I'm still, before we even get to that, I'm pretty unhappy about how long it took to get this thing. Is there a better way to do it? Yeah? If we made the word list into a dictionary. Aha, that's a good idea. So what would we do then? How would that work? So let's say we make a dictionary. What will the keys be in the dictionary? Yeah.
Make the keys into the word.
So make the keys into the words. And then what should that map to?
The integer value of how many times it occurs.
Yeah, then that key, that word, can map to the value of how often that thing occurs. Okay. And now if we think about this for a little bit, we'll realize then all we have to do is go through the whole book once, and for each word we see, we're just going to either add it to this dictionary because it's the first time we've ever seen it, or we're going to increase the counter for that particular word because we've already seen that word in the dictionary. And at the end, we'll get basically the same thing we created here, a nice histogram of words and how many times they occur. So we had the same, we got that here with these tuples, but we can get the same thing with the dictionary, right? So let's see how we might do that. So we'll define a function called histograms. And now I'm really, this is really programming in the raw here, trying to define functions actually in interactive mode. Probably get this wrong. So let's say we'll go for every word in the text that we're looking at. In this case, the text that will pass this thing is the words in Varney. So this will start with the first word, then the second word, then the third word, and the fourth word. So what should we do when we encounter, so we got this word now, and what do we need to do? Yeah. So we would like to know if we've seen it or not. So we're going to keep a dictionary that has these words in it, and we want to know if this word is in the dictionary. We'll call this dictionary H. I should have defined it one line up, but I didn't, so now I'm stuck. But that's okay. We'll cheat our way around that. So we'll say if W is in this dictionary H, then what do I do? What's that? So I increase the counter. Then I'll say H at W equals H at W plus 1. We've seen this word one more time. Otherwise, what do I do? It's the first time I've ever seen the word. Yeah. So we add that word to the dictionary, and which means we have to give it a value. 1. It's the first time we've seen this word, so it's occurred once so far. And here's where I'll cheat my way around this thing. Return H. And I'll define H as a global. I should have actually defined it in the function and then returned it, but I don't want to have to retype the whole function. So let's try this. Histogram of Varney words. That was pretty fast, eh? Yep. Don't have to define what? What do you mean the keys?
Like, don't you have to tell it that this word is...
Oh, I lost it.
This word corresponds with this number.
Well, no, we've got that. So let's go back to the text of this thing, and we can redefine it a little bit better. So there's the full text of the function the way it should have been defined the first time. So we create this new dictionary, it's empty, and then we scan over our list of words. And the first time we see a new word, or the first time when we see a word, we check if we've seen it before. If we haven't, we end up in this else clause, And that's the place where we define this thing as a new key in the dictionary. So remember, for a dictionary, the way to add a new key is you just say dictionary at that key, it gets assigned a value. So this is where we're adding things to the dictionary for the first time, and this is where we're just adding one to the value that's already there, the counter that's already there. So the keys are words, right? So I can ask questions now, like H at, I don't know, give me a word. The is a good one. 17,718 times. Give me another word. Blood. Only 117 times. Garlic? Not even once. Since we're talking about garlic, we can talk about crosses. 12 times. Girl? 54 times. If? 1,335 times. For? I don't know. Give me some words that are, well, vampire was one of them. Varpire. Vampire only occurs 22 times. Any of the old spellings, maybe? No, not there. Ah. Vampire with a Y occurs a lot more often. Teeth. Fang only occurs 3 times. Can you imagine that? I mean, this is nothing like a modern vampire story. Fang is like the main thing, the main feature of a vampire. Not even once. Yeah. It is a love story.
Is this a PG-13 rated lecture?
Use your judgment.
Can we do breast? Because that's already on the YouTube video.
Yeah, breast is already there. That cat is out of the bag. Only 3 times. So we accidentally hit one of 3 occurrences in this thing. All right. So now we've got the data, and so let's get it again just to see how fast that really was. So we can say H equals histogram VW. Pow, done, like that. There was actually a delay that I saw there, but just barely, right? We're talking like maybe half a second or something. Certainly much better than the way we did it before, which took minutes. Right, this is what we tried to do before. That took forever. So good, and that's because we used a dictionary in the right way. I mean, if we look at what this function did, it went through the list of words. There's 488,000 of them, and for each one, it just had to look to see if the word was already in the dictionary and either add it or change its value. But both of those are just fast operations. It doesn't matter how big the dictionary is. And so basically the time, instead of 12,000 times 488,000, is closer to just 488,000. Yeah.
So in the function where we're creating the histogram,
Yeah.
we check to see if the word is already in the dictionary.
Yes.
Would it be faster if we created a set to check to see if we had already had that word?
We could have done that. Let's see if we can. It's a good question. So let's redefine histogram. for words, and then just say S is equal to the set of words, and then say for S, for W in S, H at W equals 1. We know it occurs, or 0, let's say. We know it occurs, and this counter will get incremented eventually. And then we could say for W in words, H at W equals H at W plus 1. This doesn't return anything, but it does add everything to H. So let's say and then we do histogram VW. It's hard to say if that's faster or slower. Why don't I time it? Because I forget how to time things right now. But it's a similar amount of work. So basically, when we convert a list into a set like this, that's 488,000 things. So we go through the whole list, adding things to this set. Then we go through the set, that's only 12,000 things, and turn that into the initializing the dictionary. And then we go through the words again, that's another 488,000 things. But the code that we execute each time is a little bit simpler now, because we're guaranteed that the thing is already in there. Yeah.
Is there a reason you use HW equals HW plus 1 and not just HW plus equals 1?
No reason except that I never actually taught you guys plus equals. You know it from something else you've done, I guess. But, and it's, I don't do that because it can be a stumbling block, a stupid stumbling block for people who haven't seen it before. So I just try not to use it, but I have no problem with you guys using it. All right. Okay, let's quickly get what we want out of this now. So we got H as this big dictionary. And so what I think we would like to do is maybe see the top most frequent words, see if that tells us anything. We were sort of guessing, but we don't really know. So let's see if we can do that by sorting. So first thing we want to do is make a frequency list. And we'll do that by saying W and H at W. For W in H. Actually, we'll do it the other way around. Okay, so again, we're using tuples here. So we're going to make a list of pairs, so tuples of length 2. And these pairs will have the frequency first and then the word next. Somehow we're interested in the high frequency thing, so we'll put the frequency first and then the word next. And so we get a big list that way. So if we look, for example, freak at 0, we see that, again, it's that super common empty word. We don't like that one so much. Freak at 1 is funereal, occurs twice. So this doesn't tell us anything new yet. But the nice thing is freak is a list, and we can sort lists. So let's take freak and sort it. So what do you think freak at 1 or at 0 is? No. It tells us that the word 000 occurs once. And freak at 1 tells us that 109 occurs once. 212 occurs once. Well, that's not what we wanted. And so maybe what we want is, so we've sorted freak, let's reverse it. So there's the space we're looking for. 1 is the, 2 is and, 3 is to. So let's go for the 50 most common words in this great work of literature, Varney the Vampire. Nothing surprising. Anything in there that's specific to vampires? Not really. Let's go the next most common words. Were, sir, well, been, vampire. There it is, with a Y. Varney finally makes it in there 937 times. Apparently there's an important character called the Admiral. Henry's almost actually more important than Varney. And they say sir a lot. There's another character named Francis, and probably that's a character too, Flora. And let's just go 100 to 150 and see where that takes us. Bannerworth. Wow. Must be a place that shows up a lot. Chillingworth, Marchdale. Now we're getting into the names of places. And Holland, 340 times. Because that's where vampires come from. And now we're not gaining too much. There's some doctors. Probably people who get bit by vampires look sick, so they call a doctor. Okay. So I think that's a good place to leave it for today. And good luck on your assignment.